Hello everyone, welcome to Stat 479 Lecture 21. And this begins the first of probably what will be 4 lectures that correspond to lectures that are kind of meant to guide you through your project. So today will be lecture 1, and so of this set of 4 lectures, or lecture 21 in the course. All the lectures will be in the module under project. So I've already under there. There's a module on the course project on the website, and so all of these lectures will be added on that through that link. And I'll hopefully have all of them done before Thanksgiving, but we'll see how that goes. So today will be kind of the first lecture that talks about the project, and in particular, we're going to go through the guidelines and tips for the project. For today, I hope you have in front of you the 479 project guidelines, which have been on the course website for I think a couple of weeks now. And so we're going to go through that, and then what I'm planning to do for these 4 lectures is to kind of try to go through most of the tasks using a demo data set that I have and that I've already put on the website. So there's a demo data set there that I'm planning to kind of go through just to give you an idea of what I kind of expect from you guys for the project. Obviously you'll do it on a different data set, but I'm just kind of want to give you a sense of what's expected. And so today we'll go through the project guidelines, and then we're going to start to go through the demo data set. And in particular, I'm going to kind of try to go through all of the 9 tasks that are listed on the project guidelines and over the 4 lectures. And so today I'll focus mainly on tasks 1 and 2. And maybe if we get time, we might go into parts of task 3 as well. And just to kind of we're going to go through the guidelines and the tips. And one thing to kind of bear in mind, and why I've kind of separated this part of the course from the first 20 lectures, which are really going through kind of the methodology and theory behind what we're covering. I guess like when you're dealing with real data, and in particular like applied problems, and you're trying to apply the algorithms that we've learned in the course, the skills that we need are quite different from what's required for the mathematical theoretical part. So I mean, really for this implementation, there's going to be a lot less math involved, and a lot more it's going to be you're going to have to make judgment calls that are not necessarily black and white. And so I've tried to provide a little bit of a rigorous framework for how to make those decisions. But the idea is that what you've learned in the course, for the various methods and techniques that we've learned in the course, the math that you learn in that should hopefully provide you some idea of how to make those kinds of data-driven decisions as to which methods to use, how to use them, and so on. But the skills are quite different, which is kind of why I'm sort of separating it and kind of like separating this into the last 4 lectures. And so hopefully like some of that will come through in these 4 lectures. So I mean, it's not it's not going to be as simple as here's a data set, I applied these methods and these are the results. I kind of want you to also think through like why you're making every decision that you make. And so that's what the guidelines are meant to go through, and that's what hopefully the demo that I go through over these 4 lectures is going to illustrate as well. Okay, so as I mentioned, have the project guidelines and tips in front of you. I'll go through them, but I won't kind of just repeat everything that's there. I'll try to kind of just highlight the main points. So in particular, if we look at the tasks first. So for the tasks, I mean, the first one is to, choose a data set and a group. And so as I mentioned, you can work individually if you want, or you can work in groups of 1 to 4, like groups of up to 4. So certainly, that's kind of entirely up to you. I don't sort of encourage or discourage working in groups. If you feel comfortable and would rather do it on your own, then that's totally fine. If you'd rather do it in groups, that's also okay. As I'll talk about at the end, you're still required to hand in an individual report in the end and kind of clearly state what your contribution is in the group, just to get a sense of what you did in the context of the whole group. If you do it in a group of if you do it with someone else. Okay, and so actually, like task one of choosing the data set in particular is probably the most important task, actually, because how you choose that's going to potentially shape like what you do. So this is actually a very important task, and as I mentioned, as I stated on the project guidelines, I want this done ideally before Thanksgiving. So the due date for that is November 25th. So I'd like you to let me know what group you're in and what data set you're working on by November 25th. So yeah, you don't have like this doesn't mean you have to do any of the analysis or any of the other tasks. I just want to to know sort of that you've all at least thought about this before the break, and then kind of after that, after the break, you can kind of focus on completing the tasks for the project. And I kind of want to encourage you guys to all choose something that is that interests you. So in general, so the only restriction on it is that you must have at least 20 samples and at least 5 variables according to the way we've defined the number of samples and the number of variables p in this class. We'll see that there's actually the choice of p might actually depend a lot on how you do a few of the tasks earlier, and we'll go through that later. But this is just a basic guideline to make sure that we're actually doing multivariate statistics, because the whole idea of this course is that you have more than one variable that you're dealing with. And what defines a variable will hopefully become clearer as you go through the explanation of the other tasks. And so when you're choosing a data set, I'd say think carefully about what you're interested in. So if you actually already have other research projects or other things that you're doing where you're working with data, I certainly encourage you and don't have a problem at all with you using that for this project, because I think the more interested you are in the data set and in the scientific project that you're working on, the better you're going to do. So if you have a research project or you're working on a data set with maybe another professor or with another group, certainly feel free to use that because I think that's actually probably going to make your life easier, and it probably means you're going to do a better job. If you don't, some of you may not have projects or data sets in mind, and that's okay too. As I mentioned, I'd encourage you to work on something that interests you. So the most important point is choose something that interests you. It's going to make the remaining tasks a lot easier if you're actually interested and are keen to find out more about the actual data and scientific questions. So for example, some of you might be really interested in finance, and there's certainly a lot of finance and maybe stock market data available that you can choose. And so that's certainly reasonable. Some of you may have interest more in biology or neuroscience or something else. Some of you may have more interest in advertising or maybe data like Netflix data or something like that. And there's lots of different data, and so there's literally millions and billions of different data sets available online. And choosing something that interests you is something that I would highly recommend. And if you're really stuck, there are certainly also plenty of data repositories. The one I've listed in the task is, for example, the UC Irvine Machine Learning repository has lots and lots of data sets that you can choose from. So it shouldn't be hard to find a data set, but I just want you to think and try to make sure that you're kind of interested in the data set that you're looking at. And the other thing to go to is it's important to kind of go through all of the tasks that you need to complete before choosing the data set that you do, because once you see what the tasks are, that might shape the way you want to choose things, because as I said, it's not going to be quite as straightforward as just pluck a data set and just kind of run some algorithms on it. I kind of really want you to think a bit more about the underlying scientific question. So that brings us to the second task, which again is kind of very important, and this might shape the way you choose your your data set as well. So this really gets to kind of understand the data set, and more importantly, the scientific question. The scientific question behind it. So any data set that you find, whether it's something that you're working on, that with a collaborator or with a professor, or it's something that you find online. There's data isn't just collected for the hell of it. There's always kind of a reason behind why that data is collected. And so in particular, there should always be some underlying scientific question that you're looking at. So for example, if you're looking at stock price data, I mean, the underlying question there typically is can we predict whether the stock price is going to go up or down over the next period of time. So if you're interested in maybe short-term trading, you're looking at maybe whether the stock price is going to go up or down over the next day or week. But if you're maybe more interested in long-term trading, maybe you're interested in whether the stock price is going to go up or down over the next year or 5 years or 10 years. That maybe you're potentially collecting, you have data related to voting, and you might have demographic variables for different voters. You don't know all about them, but you might know, for example, where they live, like which state they live in or which county they live in, what's their education level, what's their gender, various other features. And so you might want to determine, how does various different demographic variables influence who votes or whether someone votes or who they vote for and so on. And so really think about the underlying scientific question that you're trying to answer here. So as I mentioned, as I kind of already mentioned, this is not going to be just as straightforward as you take some data and just apply algorithms to it. I kind of really want you to put it into a proper kind of scientific applied stats sort of framework where you're thinking about what you're trying to do, because that's really going to shape the decisions that you make as well. And just remember, at the end of the day, the data is just a collection of numbers. And if you don't really know where those numbers come from, whatever methods that we talked about don't really necessarily make a lot of sense. And so that's why understanding the scientific question behind it's really important. And then the second thing related to that is, understand, how data is collected or generated. Okay, so this is probably the most important thing actually in all that, is understanding how the data is collected or generated, because the way that we've typically done things in this course, and what's typically done in theoretical stats, is that you assume some underlying data generating model, a linear model, or we saw a generalized linear model, or various others, where you assume the underlying distribution of your data. And that is perfectly fine to kind of develop methods, but in the real world, your data typically never necessarily follows these models. And I remember at the end of the day, the data is just a collection of numbers. And in practice, you're going to have to deal with considerations that might kind of limit your ability to produce really random data out of it. And so, for example, if you're if you're looking at demographic variables for voters, there's going to be a lot of different forms of selection bias in there typically, because certain people are more likely to give away their information than others and so on. And so those are sorts of things you need to kind of keep in mind in terms of where the data comes from. Is it generated randomly, or is it actually kind of a very structured kind of thing? So for example, some of you may want to maybe working on text data. When people write documents, they usually don't kind of they usually just don't type randomly. There's always some, purpose behind it. And so that's potentially going to change the way that you expect the words or the phrases that you're looking at to be distributed. And so all of these things need to be thought about when you're thinking about what you're going to do. So understand how the data is actually generated, and that's kind of a very important kind of next step. And then the next task is what I kind of refer to as exploratory data analysis, and that's kind of it's it has the acronym EDA because it's such an important it's such an important step in the whole pipeline of working with real data with statistical methods. And so what this basically is that forget it, like we're not even close to kind of running algorithms yet that we've learned in class. It's just really like look at your data is basically, so look and kind of plot your data in various ways to understand it. So, for example, like if your responses or your features are continuous, you may want to plot histograms of those responses or features just to give you a sense of like, well, is the data kind of does it follow a nice distribution, or is it kind of is it highly skewed in a particular direction? Because all of these are going to give you an idea of what you want to do. For example, if your data is highly skewed one way, often you might want to, before applying these methods, like transform your data so that it's not skewed. For example, if you want it to fit a linear model and you have data that's kind of very, very highly skewed to be like maybe they're all positive and highly skewed, often what people might do is take a log transform. And you can only know that if you look at your data first. So look or plot your data before you generate it. And so this means kind of looking at the features and looking at the responses in various different ways just to understand like the basics of it. You might notice a lot of things about the data that are actually probably more important than anything you do in the modeling phase, which is just that you might notice that there's some missing data. I'm guaranteeing you that if you look at your data, there's probably something you'll notice that's a little bit odd, and that might be something you want to check up on again. Like you might say, oh, that doesn't look right. And it also feeds into step 2 in terms of how the data is generated, because if you if you assume that your data, for example, is generated randomly in some ways, you might look at your data and look at something and say, that doesn't seem random. That seems like some sort of systematic error or systematic like phenomenon that's going on. And why is that going on? And, what's the reason for that? And so that's something where, like doing things like, running, like if you use like the hist command in R to run histograms, or even just look at if you're dealing with discrete data, you might just look at you can see the distribution just through numbers. Like if you have 0, 1 data, how many zeros and how many ones are there? Because if your data is like often you might have data sets with a very high number of zeros and a very low number of ones, and that might be something else that you have to deal with. And so these are all like there's just lots of like just looking at your data in various ways is going to help shape all the decisions that you make. And then this feeds into the 4th step, which is, I guess I'll say like data pre-processing. And I'm gonna do all of these things with a specific example that I've shown you the data set on the website, and I'm going to go through that in the next 4 lectures. So then, in terms of data pre-processing, as I mentioned, you might take a lot. You might want to transform your data because it if you look at the raw data, it's highly skewed, and you might want to deal with that. You might want to remove outliers if there's some weird looking outliers in your data. You might want to remove that. Another thing that's very common in a lot of examples is normalizing your data. Sometimes you'll have, and this is again is why exploratory data analysis is so important. You might have some features that go on a scale from like -100 to 100. You might have other features that go on a scale of -0.1 to 0.1. And so kind of fitting them in the same model is going to be a little bit difficult unless you do some kind of normalization first. And so like this feeds into the data pre-processing. So like before you start to think about what algorithms you use, like at determining like if you normalize all your features, that might be a good thing to do. So and then the other thing that's also very important, and this will actually come up in the example I talk about here, is just how do you encode your features or your covariates. So sometimes the features won't necessarily be nice sort of numbers that represent something clear. You might have to encode them in a way to capture what you want in your modeling. And so those first four steps are really important. And note that we haven't even like gotten to even thinking about like anything that we've learned in the course. And that's sort of like, that's the way that most like applications work in practice, or most sort of, if you want to use statistical tools to solve scientific problems, most of the work actually happens before you do anything that you've learned in your statistics classes. And so I want you to sort of keep that in mind and make sure you do a good job of those first four steps. Then we sort of move into things related to the course. So we want to choose at least two algorithms or methods. And then, that's also related to the models. Remember that models that suit your problem. So, for example, if you have a response and then maybe like some number like 10 or 100 features, a natural thing to do might be to fit a linear model or a GLM. But then you might also like want to you might also want to do some variable selection, which means you might do a regularization with a lasso or something like that. And so there's an example of where you'd get two algorithms that we've learned from the class. And also keep in mind the all the algorithms that we learned are tied to like models. So remember the four components that we have for our kind of general thing. We have the data, the model, and then the algorithm and the analysis. And so in some sense you should write down the model that you have and then discuss the algorithm. And one of the things to keep in mind, and I we'll talk about this more when I go through the assessment and the tips, is that every single decision you make, so these will be decisions and they won't be black and white decisions that say you should definitely do this or you should definitely do that. These are you're going to have to make some judgment calls. Just make sure that you write down why you did it. So, I mean, it doesn't have to be something that is like 100% correct, or that, is that there's a right answer. As long as you justify it in a reasonable way, that is, that's all that's reasonable. And so, one of the important things about writing down the model is if you look at kind of steps 2, 3, and 4, everything that you've done in those steps should feed into what is hopefully a reasonable model to choose here. And so that's the next step, and then we kind of get to the implementation. So implement these methods in R and interpret the outputs. And this is where like that fourth component. So the fourth component of our of our framework comes in, which is the analysis. So here things are going to be very different when you have real data. Like you don't necessarily have a you don't necessarily have a true parameter that you know what that is. Like you're fitting a model and the model should tell you something, but you don't know what the ground truth is in real data. And so this is where, you need to kind of think about what does the output really mean? So is it telling us that, these covariates are really relevant? which variables are most significant. Some of the variables very, very highly correlated, and so this is where the interpretation of these of these outputs is really important. So this is the next step. So implement these methods in R and add interpret the outputs. And then this next step is also really, really critical, which is to validate your methods. So validate your methods or outputs. Okay, and so this is, this comes from the fact that we don't really, unlike the simulations you've done, you don't know the truth. And so whenever you get an output, you should always have some degree of skepticism as, well, can I trust this or not? If you want to talk to a practitioner, if you just, run your data and give them an output, they really want a sense of whether they can kind of trust that output or not. And so that's where we're going to go into a few validation techniques, which are really useful and important in practice. So in particular, cross-validation is a really widely used technique, and the idea behind it is that and the other key thing is this idea of stability, that if you perturb your data a little bit, so if you get a data set and then if you remove one or two samples from that data set, does that completely screw everything up? Because if it does, that tells you that your conclusion's not very stable, and you may want to think about that when you present your output. So that's where, and then prediction error is another one, so cross-validated prediction error, which I will talk about shortly, which is a way to kind of just at least test that your methods at least predict your data very, very well. And then, we want to, so tie your, conclusions back to your scientific question. And so this is where, the first couple of steps or the first couple of tasks are really important. So, for example, if you're looking at, the relationship between various demographic features and who they vote for, you may determine that, hey, gender is a really important feature, or, which state you're from is a really important feature, or the education level that you're from is a really important feature. And so just make sure you look at your original scientific goal or question, or maybe there's a hypothesis there that you're trying to test. And, look at your outputs and then say, well, did we address the original scientific question or hypothesis, and to what extent did we address that? And so again, this links back to the science, and we're moving away from the method. So really, the only real steps that involve implementation of these methods are really 5 and 6. And so the other sort of 7 steps that I'm going through are really more about what wraps around that, and what wraps around it is obviously very important. And then the final thing is we want to whenever you analyze some data and try to address a scientific question, it's never the end of things, because you might find something that requires future work that you haven't done so far. And this isn't something that you have to do in this project, but to actually implement in this project, but certainly something you need to at least think about is, well, what's next? So with these kind of data-driven, these data-driven approaches to scientific questions, this is always an iterative process where, there's a scientific question that you have, and then you and then you might develop some approaches to it, and then follow these steps and form some conclusion. But then there's going to be some next steps after that. So in the voting example, you might say, well, gender and state and education are all really important features in determining who people vote for. But then a natural next question is as well, what if you looked at combinations of these features? So like maybe there's some interaction between state and education level that you might want to look at, and that's not something you've looked at so far. And so that's kind of a next step. Another next step might actually not be a statistical step, but just say that, well, we need more data because we have a preliminary study that is encouraging, but we only have maybe 20 or 100 samples, and we can't really kind of do more with that. And we can't really say more until we get more data. And so that could also be another next step. So really just think about what's going on in the broader scheme of things and what next steps might actually be. So those are all the tasks that need to be performed, and I've spent quite a bit of time on them because as I said, the project does require skills that we haven't really talked about in the first 20 lectures, and I'm going to go through some of them in the next in this and the next 3 lectures, but I want you to kind of start thinking about this now. And so the next thing that we'll talk about that's covered is assessment and like tips for doing well. And again, these are all in that handout, so I'm not going to just repeat everything in the handout. So the assessment will be based on the final report, so the final report, you need to like address all of the tasks above. But what I'll probably say is that's really important is that it is important to explain to document what you did. But it is even more important to explain why you did it. Okay, so this is something that's very common, a common challenge for students is that they often spend a lot of time explaining kind of, what they did. And, that certainly needs to be in the report, but like what's probably of greater importance is actually why you actually did that. Because, as I mentioned, you're making a lot of data-driven decisions here that are not black and white. And if you don't sort of say why you did it, then, a natural question that someone will ask is, well, this seems like I can understand what you did, but why you did it doesn't really make sense to me. So make sure you kind of include that. And the other thing that's really important is clarity and precision of the presentation. So make sure you finding really good ways to visualize your results and visualize the data is really important. So I just wanted to point out. So you can look into ggplot and other plot functions in R, just to kind of if you can present like clear ways to visualize things, that's kind of really, really important. The next thing is really about reproducibility. So one of the most basic requirements of any data analysis is that it's reproducible. So someone else should be able to essentially like take your code and your report and be able to do absolutely everything that you just did. And sadly, actually, a lot of data analyses don't actually meet this bar. Like it's either that they are not explained well enough, or that things are incorrectly documented, which means that these are not reproducible. So, another group should be able to, or another person should be able to take your report and be able to actually and be able to reproduce it. So make sure results are and this is potentially one of the more important things. If you get hired in a company or something, they really want to make sure that that whatever you do can be reproduced by someone else, and that's a very basic standard that you need to meet. And yes, as I've already mentioned, justify any decisions you made. So, as I mentioned, there usually is more than one way of doing things, and so it's very important that you justify why you do what you do, and for example, like, why did you normalize the data in a particular way? Why did you choose to run this algorithm rather than a different algorithm? Just all of those things, and even a simple justification as like, I did this because like that's what I know. That's still a reasonable justification because everyone's knowledge base is different, and so that's okay. And you can even say that I did this because I only had a few days, and this is all I could do in a few days. That's a reasonable justification too. So, don't just be very upfront about why you made certain decisions. And yeah, as I mentioned earlier, there's many different right answers. So it's more about justifying choices rather than having a right answer at the end of this. And as I So you always need to connect back to the scientific problem that you're working on. So this is why it's important to start with a particular scientific question or scientific problem, because you're always connect, because you like everything that you do should kind of connect back to that, and so you should always keep this in mind. So whenever you're making a decision, whatever you write in the report, say, why is this a good thing to do for the scientific problem that I have in mind. And then the final thing is, if you do work in groups, so if you have more than one in your group, make sure you put a section which explains what you did. So every person hands in an individual report, and just explain what you did as a contribution to the whole group. Just so we can get a sense of like what each person did for the project. So that's kind of it for the overall guidelines, and hopefully some of these things might become clearer as I go through the particular kind of demo example that we have that I have here. So let's So now we're going to go through tasks 1 and 2 for example, for the example data set here. Okay, so the first task is obviously to choose a data set, which I've already done and I've put it online, but I just wanted to first explain to you where I got that data set from. So in terms of choosing a data set, so this So the data arises from a biochemistry lab that I work with. So I have a collaborator on campus, and they're interested in using kind of statistical or data-driven methods to solve some of their sort of biochemistry problems, and I'll sort of talk about that shortly. So if you look at the data just very quickly, there's 988, I guess, lines. We have strings of 8 integers, 1, 2, 3, and then binary variable 0, 1, and I'll sort of talk about what what that all means very shortly. And again, I'm choosing this data set because it's something that I'm working with, and that I hopefully know a little bit more about than just a set of numbers that I just randomly pull from nowhere, because I've had some interactions with my collaborator, and I'll and it's something that I'm genuinely interested in the scientific problem that I'm looking at. And so again, you're not maybe going to be as fortunate as that to have a collaborator. So that isn't like, so you can't just necessarily ask someone, where does this data come from? But I think if you keep asking yourself questions about, like, try to figure out as much as you can about where the data comes from, and this is where the interest in the actual data and the scientific problem comes in. That's going to be that's going to be really, really important. Okay, so now for the second task. So scientific question and where data comes from, and so, or what does data mean? Okay, so the underlying scientific question, and again, I'm fortunate in this case because I have some interactions with my collaborator, but it's a reasonably simple question to state, which is that how does protein, so the overall question is, how does protein sequence influence biochemical function? So that's the underlying scientific question that we're really interested in. So so where the data comes in is that we have eight integers, and these are 1, 2, 3 integers. That represents the protein sequence, and I'll talk about why shortly. And then the 0, 1 represents is that, so this is a binary response, is that sequence functional? So this is binary. In practice, and in reality, functionality may not necessarily be a binary thing, but they have a pretty clear. So in discussions with my collaborator, they have a pretty clear threshold as to when a sequence is functional or not. So yeah, I just want you should take a quick look at the data just to see sort of what I'm talking about in terms of the what I'm describing here, and so in terms of I guess another question you could ask is this is a scientific question: how does protein sequence influence biochemical function? Why do you care about that question? There's also tied to that is this sort of engineering question of, if you can you actually design better sequences by if you have some sequence, can you actually design it in a way by changing it so that the functionality actually improves? And that's kind of the underlying engineering question associated with this this scientific question. So can we use understanding of protein sequence to function relationship to design better proteins? So these are going to be synthetic proteins that are designed in a lab. And so the idea is that if we can use our statistical data-driven methods to actually come up with rules that tell you, hey, you should actually place this element in this point of the sequence, then, maybe you can actually improve the functionality that you're looking at. And so I haven't actually said what the functionality is, and that's different from protein to protein. And for this particular data set, there's a particular function in mind. But the general idea is that you have a sequence and then you have a binary response of 0 or 1 to say whether it's functional or not. And so now the question is like, what do the numbers represent? And this is often one of the harder questions to answer, and I'm probably going to spend the majority of the rest of the lecture just talking about that, because that's really important in determining kind of trying to understand sort of the data and the scientific question. So what are the 1, 2, and 3? So in particular, so we have here we have y is in 0, 1. So this is kind of nice. And so this is this is reasonably straightforward to interpret. 0 means sequence non-functional. And 1 means that sequence is functional. Okay. And again, I mean, I'm explaining this for a specific for this specific data set. You're going to have a different data set, obviously. So you're gonna things are going to be different, but the idea behind this sort of demo is just to show you what kinds of things you should be thinking about. So what do the numbers represent? So then the X here is the sequence of 8 integers. Okay, and so integers which could be 1, 2, or 3. And when you see things like this, there should already be sort of an alarm in your mind going off. Well, what does the 1, 2, 3 represent? Are they do the numerical values actually mean something? Are they just categories? Do they represent some kind of ordered response where 3 is bigger than 2, which is bigger than 1? And so all those different questions should already be entering your mind if you see integers like this, because integers often represent different things. And so what does that actually represent? So this kind of corresponds to how is data generated. So here, so one particular protein that's of great interest, it's, for human and other types of and for chemical processes, and then also for human processes, is it's called P450. What that actually represents, I'm not entirely sure, and it's not maybe super important, but so data corresponds to P450 sequences. So they're variations of an enzyme that's widely used for a number of different applications. And so and this is something that I only know through interacting with my collaborators. So actually finding these answers might be quite difficult at times. And so it's important that you just understand at least as much as you can. So you may not ever completely understand where all the numbers of the data come from, but just try to understand to the greatest step that you can. So the basic idea is that 1, 2, 3, they actually represent categorical features. So that's the first kind of key thing. And where do those categorical features come from? So the thing is that there are 3 parent sequences. And actually, one thing I haven't mentioned is what is a sequence. So a protein sequence is a sequence of amino acids. This corresponds to what is the genetic or what is the DNA code, but quite simply, amino amino acids can just be thought of as like, there are 20 letters. There's like A, I think B might be, like C is certainly one, and V, and like there's 20 letters of the alphabet that represent kind of different, that all have kind of different chemical properties, and it comes back to the genetic code. And so there's 3 parent sequences of what is it? We'll see why I call them parent sequences shortly. 3 parent sequences of length about 480 amino acids. So essentially what you have is you have like, parent 1, parent 2, and parent 3, and then they might have like, A, V, C, and then, V, T, V, T, Z, whatever, like, and then like G, U, like L, blah, blah, blah. And again, these letters just come from the genetic code, and there's, these are length, the total length is about 480. I know the exact number, I think, is about 490 odd, but like that's not super important. And so that's where and these, so 1, 2, 3 correspond to each parent, and then like why? Then the question is, why is the length 8? Okay, and this comes exactly from like how the experiment was conducted to actually generate these different sequences. So what's going on is that you're actually kind of cutting the so you cut each sequence in 7 places, and so you cut each sequence in 7 places to give you so I'll just call this 1, 2, 3, 4. Okay, to give you 8 subsequences for each parent. Okay, and so each string of length 8, and so I guess like the next thing is, so you first cut and then you recombine these substrings to get new sequence. And this is probably like easier to actually explain with 1 or 2 examples. So, for example, if we have the sequence like 1, 2, 3, 3, sorry, not 4. It only goes up to 3. 1, 2, 3. 1, 2, 3, 3. 1, 2. So 1, 2, 3, 4, 5, 6, and then 1, 1. Let's say we have that as our sequence. So each of those is this. Then what that's basically saying is you've got a sequence that looks like this. So so you recombine the sequences. So let me just, again, cut them into 8 pieces the way that's done. Okay, so what you're basically doing is you're taking for the first part, you're taking the sequence from 1. For the second part, you're taking the subsequence from 2. Then you're taking the subsequence from 3. Then you're taking the subsequence from 3 again. Then you're taking the subsequence from 1. Then you're taking the subsequence from 2. And then you're taking the subsequence from 1 and 1. So there's essentially an assay or an experiment is conducted such that so this is like, we'll call this like position 1, position 2, position 3, up to position 8. And so so each sequence so each sequence, we'll say X, represents how substrings of the 3 parents are recombined. Okay? And so this is performed using an assay, and I won't go into the details of that because it starts to get a bit technical at that point. But you can think of these as randomly recombination is approximately random. So recombination is approximately random. And then, so note that total possible sequences is 3 to the 8. And data set has 988 sequences, which is 3 to the 8's about 5,000 roughly. So we have about sort of a fifth roughly of the total number of sequences that we have. And so that just gives you an idea of what that represents. So you can, I mean, the upshot of all that is that we have X1, X2 up to X8. But the thing to keep in mind here is that like these XJs are categorical. And that's something we haven't actually talked about in this course so far. Categorical, and we need to treat categorical variables differently to binary continuous etc. And so, and I mean, the reason for that, if you think about it, is quite obvious, because if you have a 1, 2, or 3, it's better to probably think about it as like an ABC. The numbers 1, 2, or 3 don't actually mean that, the 3 is kind of like a higher value than 2, which is a higher value than 1. They just represent different parents. And so you need to kind of factor that in, because if you fit a regression model or something like that with categorical variables that where those numbers actually mean 1, 2, and 3, then you're going to get some misleading kinds of results. And so that'll be it for what I covered today. So it's kind of gone through tasks 1 and 2. The next lecture will focus a lot more on tasks 3 and 4 for this particular demo or application. But one thing to kind of keep in mind is just, I've only skimmed the surface, but that's sort of how much depth is really required in terms of, that's how much depth you should strive for when you're thinking about like the first two tasks of understanding the scientific question and where the data comes from. So what do those numbers or what you read in the data actually mean? So that's like, this is actually one of the more important steps in this whole procedure. Okay, so yeah, I'll go into more detail on the later tasks in the next lecture. Okay, thanks very much.